This lesson is on simplifying radicals. We've simplified radicals before of perfect squares, but now we're also going to be looking at non-perfect square roots. So the objective of this lesson is that you can simplify square roots using what's called a prime factor tree. So for your first fill-in, a prime number is a number that can only be divided by 1 or itself. So go ahead and fill in the blank, the word prime number. So let's look at some examples of some prime numbers. Let's list all the prime numbers that we know between 1 and 20. Now 1 is prime because the only number you can divide 1 by is 1, or itself, which is 1. But let's find the ones that are in between. So these are 2, 3, 5, 7, 11, 13, and 17. Using this method of simplifying radicals, you're mainly only going to need to know the 2, 3, 5, 7, and 11. I would memorize those numbers, and on the top of any pages that you see radicals that you need to simplify or see the word simplify in the directions, I would write those numbers at the top of your page. 2, 3, 5, 7, and 11. It's a good idea, though, to still learn your prime numbers at least up to the number 100. This will help you when you're simplifying fractions if you don't have a calculator, to make sure that you know that you've reduced a fraction down all the way, because whenever you get to a prime number, you know that the fraction can't be reduced any further. So when you don't have a calculator to solve square roots of numbers, a prime factor tree is used to find the perfect roots of any numeric radicand. So I say numeric radicand, so those with numbers on it. If you see letters underneath your radical sign, then you will still use this method with the numeric part, but the variables you will do something a little bit differently that you'll learn in Algebra 2. So to do this, there's 3 steps. Underneath the radicand, you will first draw what looks like a little caret to split it. So I'm going to start demonstrating this for you. So I'm going to draw this caret underneath the 81. Now, we know from previous experience that the square root of 81 equals 8, right? Or I'm sorry, not 8. How about 9? Equals 9. But let's prove that here. So let's work on creating what's called the prime factor tree. You draw your caret underneath your radicand, the 81. Then you'll write the smallest divisible prime number on the left and its factor pair on the right. So what I mean by that is look at the number 81. Starting with the smallest prime number we know, 2. Can 81 be divided by 2? No. We know that any number that's an even number can be divided by 2, but if it's an odd number, you can't. So it's not divided by 2. How about 3? 81 divided by 3? Sure it can. So we write the prime number 3 on the left and its factor pair on the right. When I say factor pair, is basically take 81 and divide it by 3. The answer is what goes on the right. I am going to cheat a little bit and just use a 4-function calculator here for a minute. So 81 divided by 3 is 27. And 27, can that be divided by any prime number? Start again with your 2. Can't be divided by 2. How about 3? 27 divided by 3, sure, is 9. What you're going to do every time, it says under the radical, you draw your factor pair. In step 3, if the factor pair is not prime, then we'll repeat the steps, and that's what I did here. The number 27 is not prime, so I had to divide it by the prime number again. Is 9 prime? Nope, that's not on my list. So I need to split that again. Can 9 be divided by 3? Yes, 3. If the answer on your right is a prime number, for example this 3 here, then you know you're done. We've finished creating the prime factor tree. I'll show you next how this is used to find out the square root of 81, but let's practice making prime factor trees of some other numbers. In the next one we have 2025. Now I know that this is a perfect square root. If I used a calculator I would be able to figure that out. But without a calculator I just don't know off the top of my head what the square root of 2025 is. So let's make the prime factor tree of 2025, and then like I said in a minute here I'll show you how you can figure out what the square root of that number is then from that prime factor tree. Alright, so we start from the beginning of our prime numbers. Can it be divided by 2? No. Can it be divided by 3? Yes. 2025 divided by 3 is 675. Kind of big. Yeah, I used a calculator. That's okay. 675, can I divide it by 3? By the way, do you know your rules, divisibility rule of 3, to know if a big number like that is divisible by 3? What you can do is just simply add up the digits. Sorry, let me try a different color here for you. You can see what I'm doing. 6 plus 7 plus 5. That equals 18. I know that 18 is divisible by 3, therefore I know that big number 675 is can be divided by 3. Then I grab my calculator out. So I saved myself some time by knowing that divisibility rule. That's how I was able to quickly look at 2025 and know that that number is divisible by 3, because 2 plus 2 plus 5 is equal to 9, and I know 9 is divisible by 3. Okay, so if you know it's divisible by 3, go ahead and get your calculator out and divide it. 675 divided by 3 is 225. Well, how about 225? Can you divide that by 3? Well, 2 plus 2 plus 5 is 9 again. Oh yeah, so that number should be divisible by 3 as well. As you can see, your factor trees could get quite large, so if you have a worksheet of these problems, you might want to do them on a separate sheet of paper, otherwise you'll need to write pretty small. So 225 divided by 3 is 75. And 7 plus 5 is 12. 12 can be divided by 3, so let's do it again. 75 divided by 3. Oh, there's 3/4 and a 75 cents, right? 25. Alright, 2 plus 5 though equals 7. And that is not divisible by 3. So we need to go to our next prime number. We've done our 2's, 3's, we're ready for our 5's. Can 25 be divided by 5? Sure it can. 25 divided by 5 is 5, and 5 is a prime number, so there we're done with that factor tree. I may have to recopy that in a little bit when we go down below. The next one, square root of 125. If we make that into a prime factor tree, let's split it up. Can we divide it by 3? Well, 1 plus 2 plus 5 is 8. That can't be divided by 3. And I already crossed off 2 because 125 is not an even number. So let's try 5. Well, the number ends in 5, so I know it can be divisible by 5. 125 divided by 5 equals 25. 25 can be divided by 5, which is 5, and that's a prime number, so I'm done. So I've made the prime factor trees of all these. Well, how does this help me find the square root of a number? In your next blank, a radical's index, index, is located above the check mark symbol of the radical. For example, when you have a cube root, like cube root of 27, like that, that little number that's above that check mark is the index. So if you have a cube root, the index is 3. If you don't see a number above your check mark, for example, the square root of 81, your index is always 2. Now, in this course, we are only going to look at indexes of 2 or simplifying square roots. We're not going to go any further with our cubes or anything higher. That you'll see some of that in Algebra 2. So, let's simplify the square root of 81. Let's follow the steps that you see down below. This is assuming you've made your prime factor trees. Oh, I didn't write on there. That's supposed to be a 2 there. Circle and count the perfect roots, the identical primes in groups of the index. So because we're doing the square root of a number, our index is 2, we're looking for pairs of the same prime numbers. For example, I have a pair of 3's and another pair of 3's. In the 2025, let's look at pairs of identical prime numbers. Well, there's 1 pair, 2 pair, and there's even a 3 pairs there. It's pairs of the identical numbers. In the last example, we only have 1 pair of 5's. The last 5 of the prime numbers, it doesn't have another 5 along with it, so it's not part of a pair. We're not going to circle it. So in the second step, it says to pull out the perfect roots of the radical. What we've done is circled our perfect roots. We have a perfect root of a 3. In fact, we don't even just have one of them, we have 2 of them. We have 2 groups of 3's. In the 2025, I have 2 groups of 3's and 1 group of 5. Do you see what I did there? I wrote it in exponential form. The base of my exponent is the number that's the prime number that's repeated. The power of that, or the exponent, is the number of groups. In the last example there, I have 1 pair of 5's. Those are going to be pulled out of the radical. You can simplify those. What is 3 to the second power? Well, 3 times 3 equals 9. Because that's the only thing left over, that's the answer. The square root of 81 is equal to 9. So we just proved how you can find the square root of 81. Well, let's simplify the 2025. We have 3 to the second power, which is 9, times 5 to the first power, which is just 5. Any number to the first power is just itself. Well, what's 9 times 5? 45. So that's what the square root of 225 is equal to. Now in the last example, we have 5 to the first, which is equal to 5. So we pulled that out. But in the last step, it says multiply any leftover primes and leave it inside the radical. We have this 5 that's left over in the last example here, that 5. There's no other numbers that are prime numbers that are left over, so we don't have anything else to multiply with. But what you'll do then in your final answer is you'll write the square root of 5. Had there been any other prime numbers left out of our circles, we would have multiplied them together and wrote underneath the radical. So the square root of 125 is 5 square root of 5. Let's practice some more of these. Turn to your guided practice and I'll do several of them with you. We actually already just did the square root of 125. That was one of your examples. So let's go to problem number 2. Square root of 192. Okay, so we'll do the same thing. First thing I would do to start off on the top of your paper is list those prime numbers, just so that you have them for reference. What were they? 2, 3, not 4, 5, that works, 7, 11, and you could probably stop right there. Very rarely will you go past the number 11 with the prime numbers when you make a prime factor tree. Alright, 192, can we divide it by 2? Of course we can, it's an even number. So 192 divided by 2 equals 96. 96 is also even, so that can be divided by 2. Equals 48. 48 can be divided by 2. By the way, I'm just leaving that number in my calculator so that I can quickly divide it by the next number. 24 divided by 2. Oh, now I can start to do them in my head. 12. 12 divided by 2 is 6. 6 divided by 2 is 3. Oh, 3 is a prime number, so I'm done. That's the prime factor pairs. Alright, now I need to find groups of the same number. I have 1, 2, 3 pairs of the number 2. Now be careful, don't do this. It's of the number 2, that's the prime. And how many pairs do I have? I have 3 of them. I have this 3 that's left over, so that stays underneath my radical. I do need to simplify whatever's out here. So 2 to the third, that equals 8. Square root of 3, or sorry, not 8, I didn't mean to write that, 3. So the square root of 192 is 8 square root of 3. Let's try another one. This is problem 3 on your guided practice. All right, 288, it's an even number, so I know it can be divided by 2. That's 144. You should be able to do that in your head. That can be divided by 2. Well, 14 divided by 2 is 7, and then 4 divided by 2 is 2, so 72. 72 divided by 2. $36. 36 divided by 2. Equals 18. Should be able to do these in your head pretty easily now. 18 divided by 2 is 9. 9 can't be divided by 2, but it can be divided by 3. And 3's prime. So we're done. That's the whole factor tree. Now we need to look for our pairs of numbers. We have 1, 2, 3 pairs of numbers here. Okay, now be careful. Here's how we need to write this. We have identical 2's, and we have 2 groups of them. 2 groups of 2's. We also have a group of 3's. I'm going to write a little dot there because what you're going to have to do is multiply these together. We have one group of 3's, and then we have this 2 that's all by itself, so it stays underneath our radical. We do need to simplify all of this. 2 to the second power is 4 times 3 to the first power is just 3. Just keep on copying the radical 2 down. 4 times 3 is 12, radical 2. So that is your final answer, 12 radical 2. You'll find that when you're simplifying radicals, if there's a ton of them on your page, that you're going to be simplifying, it seems like the same numbers over and over again. So what I would do is start making a list, maybe in your notebook, of some of the prime factor trees that you've already created. That way you can go back to them. Because maybe later on they'll ask you, oh, what's the square root of, say, 72? Well, if you've done this prime factor tree before, then all you would need to do is copy down or look at a prime factor tree you've already done before. Just look at that part of it. Kind of saves you some time. Alright, I'm going to do another one with you, but I would like for you to go ahead and push pause on your video and you give it a try and then push play, and let's compare. If you get stuck, then just push play and watch until you're basically unstuck, and then compare your final answer. I'm at least being nice to you by having you do problem number 4, which is only the square root of 54. At least it's a smaller number. Okay, so go ahead and push pause, you try it, and then push play, and let's see how you do. Okay, square root of 54, you ready? Did you divide by 2? you can get 27. And then that couldn't be divisible by 2, but you could divide it by 3, which is 9. And 9 can be divided by 3, which is 3. So how'd you do on your factor tree? Alright, now this might have been a little trickier for you getting your pairs. I only have one pair of 3s. So one pair of the number 3. What do I have left over? Well, a 2 and a 3, or 2 times 3. I guess I shouldn't have let you off on your own just right away. Give you an example of this type. Alright, 3 to the first is equal to 3. Square root of 2 times 3 is 6. So that would be what your final answer is, 3 square root of 6. Now I don't expect that you got that one right away because it was a little bit different from the previous examples. So let's do some more. Go ahead and do number 5. I think you can do this one though. Push pause and then push play when you're ready to check. Okay, let's get ready to check. You make your factor tree the same as mine. I knew it was divisible by 3 and get 25. 25 can be divided by 5, which is 5. So pretty simple factor tree. Alright, now I look for my pairs of identical prime numbers. I have one pair of the number 5. And I have a 3 that's left over, so it stays underneath my radical. So that's basically what it is. 5 square root of 3 is your final answer. How'd you do? I'm not going to let you on your own just yet, so let's go ahead and do a couple more. Go ahead and start number 6 and let's see how far you get. 448 can be divided by 2. 224, which can be divided by 2. 112, which can be divided by 2. I think it's 56, just a second. Yep, 56, which is divisible by 2, which is 28. 28 can be divided by 2, which is 14. 14 can be divided by 2, which is 7, and 7 is prime, so we're done. Alright, how many pairs of numbers do we have? We have 1, 2, 3 pairs of the number 2 and a 7 left over, so that stays underneath the radical. 2 to the third power equals 8. Remember, that's not 2 times 3, it's 2 times 2 times 2. Square root of 7, so that's your final answer. Think you got this yet? I'll do one more with you, and then you can finish the rest of the guided practice and then click on the self-check and correct to see if you got the rest of them right. Ask your instructor if you need additional help. Alright, so you could try number 7. Found out it can't be divided by 2, but it can be divided by 3, and you should have got 49. 49 can be divided by not 3, but it can be divisible by 7, because it can be divisible by 5, which is equal to 7. Alright, and 7 is prime, so therefore I'm ready to look for my pairs of numbers. I have one pair of the number 7 and a 3 left over that leave inside the radical, so 7 to the first power is just 7, square root of 3. That's your answer. Alright, finish the rest of the guided practice and then check your work and ask if you have any questions if you didn't get the correct answer.